Hello and welcome to this debugging session with Symflower. Today we will take a look at how you can use unit tests to easily find and fix bugs. To get started, there is this quote by Dijkstra, and he says that program testing can be used to show the presence of bugs but never show their absence. And this tells us already how testing relates to debugging and bugs in general. So he says that even the best test suite can be flawed and bugs can go unnoticed by them. But he also says that tests can help us find bugs and show that they are present. So this might be correct. So you might be right with this, but if we know that there is a bug already, how can unit tests help us fix it? So how does knowing that a bug exists helps me if it takes me hours to find it? And this is what we will be taking a look at today. So first I will go into a little bit of a history excursion about what is Symflower for a second. So a brief answer to what is Symflower is. Symflower is a software development productivity tool. So that means that we want to save developers time and make them more efficient. So this also includes generating unit tests automatically to find bugs and security issues. And while this may sound like magic, this is built on top of a very well-established research topic called symbolic execution. And I will quickly go into what symbolic execution does or how it works. So this is a technique invented first by James King in 1976, so quite old actually. And the idea is we want to analyze a target program, so an input program that we get from a user, and we want to find bugs or problems. So what is then done is we do a symbolic exploration, and that means we look at every potential execution path of this program. And we replace the inputs to the program with symbolic placeholders. So this is similar to variables in maths. And we can then use a mathematical reasoning engine to essentially inspect all of the possible paths and see which one of those are reachable in practice. And then what we at Symflower do on top of that is we generate unit tests from the solutions we get. So this is not part of King's original design, but this is what we do as well. So to show this in a very quick and dirty hand example, this is rather for intuition. If we have a program with some input I that we increment, and then we check if this I is then greater or smaller than 1 or equal, we see here if the I is greater than 1, we return 0, so we jump into this if condition, and if the I is smaller than 1 or equal 1, we return 1 because we jump over the if. If we do this symbolic exploration, this means that we replace the input I with some variable x and then propagate this through the program. So if we increment the I, so I plus 1, we also need to increment the x plus 1. And then we look at these conditions. So x plus 1 greater than 1, the case where we jump into the if, is then the case where x plus 1 greater than 1. And the other case, if we're interested to jump over the if condition, so I smaller or equal than 1, this is where actually x plus 1 is smaller or equal than 1 because it was incremented. And this leaves us with two formulas. And if we then use math to solve them, we can see the equation x plus 1 greater than 1 is satisfied, for example, for x is 1. Because if x is 1, 1 plus 1 is 2, which is greater than 1. and for the other way around, x is 0, then 0 plus 1 is 1, which is smaller or equal than 1. And from these solutions here, we can then generate unit tests. So we can say, okay, if the input to the program is 1, we expect, because we inferred this, the output to be 0, because that's what happens when we take this path here. And if we set the input to 0, then we will not jump into the if condition, jump over it, and this return 1 will be triggered. So we expect that the result is 1. And the nice thing is that, so this on the slides here, we can see this whole right part here, the reasoning engine and the symbolic exploration are grayed out. And this is also not visible to the user. So the user just gives us the target program and we generate unit tests from it. Now there is, of course, more to this. There is the original paper by James King, which is very nice and concise to read. It's also only a few pages. And we have also on our website information about how symbolic execution works. So more technical blog posts, how this functions in depth, and also how this compares to other testing techniques, such as fuzzying, for example. And so from the invention of symbolic execution in 1976, I want to jump to the founding of Symflower in 2018. So the company exists since then, and we are 10 employees now, and we won several awards, Austrian startup awards, and we basically focus and are interested in all the things testing. So test generation, problem detection, debugging, code coverage, and also smart unit test templates. And we are present on social media and GitHub, and you can reach us there as well. So part of a workshop, debugging with unit tests. This is, it's possible to follow along yourself. For that you just need to head over to get.symflower.com and yes. So you will be able to choose your IDE of choice, or your for the terminal also, and that's how you can install Symflower. We are available for free for Linux, Mac OS, and Windows. So what we will look at in the workshop is a hash function. So a hash function is some function that takes an input and transforms it into an output, just like any mathematical function from one domain to another. And there are different requirements to a hash function depending on the context. So for a database, for example, the hash function must be fast. For some security critical context, it must be hard to reverse engineer, and so on. And our hash function will, of course, be neither of those, or it may actually be fast because it's only 3 iterations of a loop. So this is baby hash. This is in the Go programming language, but the source code is also there for Java. So what we do is we take an input, an integer, and we want to generate a hash value for it. So to do so, we divide the input by a divisor, and then update the divisor with what's left from the input. And we do this 3 times over and over again to generate the hash, and then return what's left of the divisor as hash value. I have this here also as a Go project. So this is a hashing package, and I also have a main function here that just takes the first input to the command line, passes it to the function, and prints the result. There is a make file here that you can copy the commands out of, but I need to go in it to make, whoops, go mod init debugging to make this Go module, and I also executed go get github testify, which is the testing library that's commonly used in Go that we will use later. So now we can run this, and for example I can use a very large number here, and the hash function will then process this and give me a hash function, a hash value. And we can try this with a lot of different values as shown on screen, and we already see hopefully that this is not a perfect hash function, because there is already a correlation between high numerical values here, so 9541 is very high and results in a hash value of 3100 and something, and 3700 results in a lower hash value numerical wise, and 5000 is somewhere in the middle. So this is by far not a perfect hash function, as we can see. But we can assume we published this somewhere to GitHub or on Reddit or in our programmer Discord group for people to play around with and to maybe reverse engineer. And then let's pretend that 1 week later a company, like for example a bank, calls us, and they call us and tell us that they actually used this this hash function, and they tell us that it's super easy, it's only a few lines of code, so they use this, but it crashes their system for one kind of input. So we have our first bug report, and they tell us that with an input of -17 this whole thing explodes. So we can try this also out locally. If we then run this with -17, that indeed Go then tells us that a runtime error occurs with an integer division by 0, which might already give us an idea of what's wrong, but let's pretend we don't, and we want to fix this for good, and we want to have a plan how to fix this. So our plan is to first find a reproducer, so that we can we have a reproducer already, but it would be nice to have an even simpler one, or to know if this is the simplest reproducer, or if there are other cases where this problem occurs. Then we will fix it, and we will see that with the help of unit tests we will fix it without breaking something else. So the first step here that I will do is close the terminal, and actually by using Symflower I can, instead of writing the unit tests, just generate them automatically. So this command in Visual Studio Code will spin up Symflower, which in the background is gonna do the whole symbolic execution business, and after a few seconds we can see the unit tests here as they would be written in Go by a human. And there is this test case that tells us if we input 0, we get a hash value of 3, which looks alright. So from this proposal of tests by Symflower, I will add this, and this will add it to our actual unit test suite. And then there is also this test that Symflower generated and found that tells us that for -9 there occurs a division by 0, which already sounds very familiar. So I will close the proposal here, and we can actually see that we have a test file here now that includes the test case that we selected, and we can run this. So this will execute the go test command and tell us that this actually works. But with -9, we see that there is also the integer division by 0. So maybe I want to include that also in the test suite here, but I already closed Symflower. But what we can also do here is if we change back, I don't want to save this. If we change back to this with the comments here, I can add a unit test for the function, and this will add an empty template here. So this will just modify my existing tests and make it easier for me to get started. And I will just manually type the -9 here. And I don't want an expected value because I know this will crash anyways. So if I run the tests now, the tests crash also with the division by 0. Right, so we have now a unit test suite that was partly generated by Symflower and partly written by us, but also we have seen that this corner case was found by Symflower. Going back to the presentation, with this unit test, we now managed to freeze the behavior of our program. So we now have a fixed specification of what should work, at least. So this example should work because it's just the most simple case. And we also have some edge cases that we can debug. So whenever I change something, hopefully the tests should pass at some point. And I will actually also, since I know this is the bug report, use Symflower again to add a unit test for the function and add -17 here, because this is also something that apparently crashes the program. Right, so let's figure out what's wrong. So with -9 as an input, we divide it by 3 because 3 is the initial divisor. And then we update the divisor. So 3 minus 3 is then 0, which leads to the division by 0. So this -9 is actually a problem here. And if we do the same thing with -17, we can see this is a similar problem. So -17 divided by 3 is -5. If we update the divisor, 3 minus 5 is -2. And then in the second iteration, we update the input again. -5 divided by -2 is 2. And finally, if we update the divisor one more time, -2 plus 2 is 0. So this is again problematic here. So we've seen that -17 and -9 here, what we added in the unit test suite, are actually the same problems, and we should be able to fix them at once, hopefully. So my proposal here would be to just say, okay, the divisor is can potentially be 0. Why don't we just flip the division, and then the divisor can become 0, and we are all happy, right? And I can even try this again for our crazy high value, and we see that this is even more problematic now. But let's check our tests, and they are all also failing. So what's happening here is the input we have the test case that the input is 0. So we will reach this immediately, which is problematic. So with this easy potential fix, the divisor can become 0 and the input cannot become 0, and our tests are saving us from just using this fix because they fail. And as we've seen, there are even some other problems where other hash values can then also lead to problems. So this test case now fails. So one potential fix would be to just revert this and just catching the case where the divisor is 0, and then just saying, well, I will then just reset it to 3 to its initial value. And then we see that the tests now not crash, but they don't crash. But since we don't have some expected values here, they also don't pass. So what I will do here is actually just delete the tests that we have and just let them be generated again by Symflower. So this will again spin up Symflower, and we have seen now that with this fix the divisor can be 0 and also the input, which now all our tests pass. And we will see here also when Symflower is done that it generates a test suite where our original test is present, that still works, and also -15, the hash value results in 3, which is exactly the case where the divisor eventually turns to 0. So we fixed this bug. We are very happy now. We made it. There's only one problem because there are a lot more bugs to fix. There are probably, a handful more. And the takeaway message here is no one writes bug-free code. We are humans and we make mistakes, and so there will always be faulty code. That's just, there's no way around it. And debugging can drive you insane, can drive you crazy, and can take a lot of time. But we have to do it. So we need some tools and workflows to enhance our debugging workflow to not drive us insane. And we have seen that unit tests give us a repeatable source of checking quickly if the assumptions we have on the program still hold, and if everything still works as expected, and if the bug is still present or fixed, it's easy to run them again and again. And we have also seen that they can help us in case we break something that already worked, and they of course are helpful to catch bugs before they hit production. And through Symflower we don't even have to write them manually anymore, but we can just generate them. If you have some questions or some feedback on this workshop, please let us know. Thanks for checking it out. Thank you so much for your attention. See you.